Hello again and welcome back to this Introduction to ASAP tutorial series. This time we will be doing a build to show the features of chromatic dispersion. Chromatic dispersion, if you'll remember, is probably as a kid you probably had a prism and shined light through it and saw how white light dispersed into different colors. That is what we're going to be modeling today. We will be shining light through a square lens. So that's another feature you can make in ASAP, and we will be able to see how our system can model a white light source or a polycolor light source. This is a good way of being able to just model something, like especially if you're making binoculars or camera lenses and you are worried about the chromatic dispersion that could be inside the product you're trying to develop. So without further ado, let's begin. Now then, we will begin, of course, with a brand new ASAP screen to start out the system. And we're going to start by setting up our system settings. So we will go here, and we will go here to System Settings. Double click this, and we will look at the optical model. Now, for our case here, we will be looking at wavelength and power. First and foremost, we will have the basics default wavelength of 55 nanometers or 0.55 microns. So be sure to have this at 55 and here at microns. You can also select what graphical power unit. We're going to go with watts, but you can select between watts and lumens. And we're still going to keep our system unit in millimeters. This system unit means to define the units of the actual physical build we'll be making. So that's what that defines over there. Now we will go into interpolation wavelength selection, because this allows us to define the types of wavelengths which will be used in our system. We're going to go down here to auto-generate wavelengths. So what those wavelengths we're going to do is just through the visible spectrum, 0.38 to 0.78. And let's do 41 because that will allow us to do that. And when we press auto generate, you'll see we get an error because only a maximum of 40 wavelengths is allowed. As much as I would have liked one for every nanometer of length, at the end of the day, we have to choose a smaller unit. So let's go with 21 and auto-generate. And they're nice, evenly spaced wavelengths, 0.38, 0.40, and it will, needless to say, it will get the job done. So we have the interpolation wavelength selected, and we have our system set up to go to work for a polychromatic light source. Next thing we're going to do is we're going to start defining our variables. So first we'll look at our lens source, and we're going to keep everything in caps. So LENS, diameter, and let's go with 63. Next we'll go with lens curve. Now for the record, despite the fact that I sent it as lens diameter, this will be a square lens. It's just how I named it before, so what can I say? I'm keeping it. So we'll set this to 65. Lens space 60. Detector size. Detector. And let's set that to 60. So with that, let's just apply these changes, and now we have variables. Let's double click on it to make sure they were saved. Yes, they were. Now we're going to go with our geometry. Now let's insert a geometry branch, and let's call this Chromatic BLD, Chromatic Build. And let's insert geometry. Let's insert geometry branch and begin with Singlet. If some of you have seen our radiometer example, this is very similar to that, albeit it provides other fun stuff, let's just say. So insert geometry branch. Let's go with detector. Yeah, this should be simple enough. Now, under Singlet lens, we're going to insert geometry, and we're going to go with optical. And so optical 1, z equals 0. Let's go with lens, and we will go with lens curve here. And this one, I just had to check my notes. We're going to go with z equals 0, lens curve, and we're going to call this one front. Now this is where things are going to get interesting. Rather than an elliptical aperture, let's have some fun and do a rectangular aperture. And semi-major axis of lens diameter divided by 2. And lens diameter divided by 2. And press apply. Let's see what we get here. We get this very interesting curved square. And let's do something, and we're going to go here, right click, insert geometry. We'll go back to optical, and this time let's select back. And this radius of curvature we want negative. Let's put location at, let's call it lens space. And we'll use the lens space as this being the space in between the two lenses. And negative lens curve, 0, rectangle, lens diameter. Yeah, everything looks like we want it to be. Let's apply, and you'll see that you have these very interesting shapes. I have obviously made this a bit of an exaggerated curve, but that just makes the chromatic dispersion look nicer. So with that, let's insert one more geometry, and this time we will insert geometry, and this will be a tube. And so tube, let's call this edge, bound by two curves, z equals 0. We'll go with lens diameter divided by 2. Lens diameter divided by 2. Lens diameter divided by 2. This is because, again, these all have the same feature. And lens space. And we press apply. That's strange. Huh, it's a circle. Well, that sucks. I wanted it to be a square. I wonder how we can do that. Let's press modify. Oh, hey, there's a curve type here. 0 for ellipse, 1 for rectangle. Let's see what happens if we press 1, 0. Okay, that's getting better, but yeah, that's not what I wanted. Albeit it is an interesting shape. Let's modify. Start curve type, end curve type. Let's go with 1, 1. There we are. And thus we have this wonderful system inside a box. Now, I want to end it at the two curves, so let's go with bound. And we have the front and back. Let's go plus for the front, negative for the back, and apply. And thus, yeah, I'm liking this guy. I think it's a good shape. And let's see where we can go from here. Now that we have our shape all set up to go, we want to define the media, because right now this is a geometrical shape, and we want to select the media. So let's go back to our singlet, select media, air, and let's go with fused silica. Air and fused silica. And we will select the coating as being transmit only, and let's press apply. And with that, we have it all set. Next, let's minimize this guy, and let's start setting up our detector. So we insert geometry here, and we're going to go with a plane. And with our plane, we're going to set it at plane 1. It's going to be orthogonal to the axis, but for location, let's select detector position, det pos. Aperture will be rectangle. Semi-major axis will be detector size divided by 2. And we'll Control C, Control V ourselves. Let's press apply. That's looking nice. Let's see how we can go from here. So let's select the light source that we want to work at. So we have our sources, and now we want a rectangular source. So we have grid rect. So we have Z, 0. Let's go with 11 by 11. I like 11 by 11. Nice prime number. But I don't know if I like this row start and row start. So we have source size for that. Source size, divide by 2. Yeah. And row stop being source. So stop, divide by 2. V, Control V. Now, the one thing that's important here is we want it to go from negative to positive. So negative, positive, negative, positive. So now that we have this set up, we'll have the total flux of 1 and wavelength being 550 nanometers. And we'll keep the ray type as being collimated. And with that, let's press apply. For the record, there are multiple types. Collimated is just, it's a good system that just creates a collimated light source. Now, you'll notice, let's jump back to it real quick. You'll notice here that we have the wavelength of 550 nanometers by default. And you're like, wait, I thought you said this was going to be a chromatic wave, a chromatic source. Patience, let's get to that. So we press apply here. We press multi-wavelength source. And this is what allows us to define our poly source. The poly source that we're going to go with, let's go with D65. And total flux, 380 to 780. And yep, total flux, number of wavelengths. Let's go with what we had before, which was 21, that we already defined in our settings, and press apply. And with that, we're going to go to, we're actually going to skip the source analysis. You can do it. You know, it's a good way to do a sanity check, but let's just straight to trace, because right now we're mainly doing the build to show its qualities. So let's plot rays. And we wanted to do all rays, and we wanted to plot the geometry. We'll go with facets, display, and Y and Z, and 0, 0. So let's press insert, and trace analysis. Actually, before we jump to trace, and so right now we'll just be looking at an image of a source just going through the system. So let's run our optical system. And you see all the colors of the rainbow. And it hits our source very nicely. I must say I quite like that. And you can see here, if you zoom into these colors right here, you'll see that for the most part, they're all monochromatic pink. But over here, you'll see how the colors diverge. And you can see when you look at the arrows that there are multiple wavelengths. So let's go back to our ASAP plot viewer, and you can see the rainbow of the sources. Now let's go to trace analysis, and let's consider objects. Again, we don't want the front, back, or edge, so let's unselect these. So what we have is chromatic detector plane 1. Let's press apply, and let's run our system again. And it ran. And let's consider the irradiance again. For vertical 51, apply, and let's go with picture and see what we get now. And thus you can see the spread of it. The red shows greatly highlighted areas, and over here you see how the energy drops off. This is because it spreads. So here the source is very much together and it spreads out as it goes further out. So you can see this display here from minus 44 to 44 millimeters left and right. Now you'll notice here in the picture that we made, so we can also see these pictures right here of the source. So you'll see right here, all of them are basically collimated at one location, but the further out we go, the further spread out our system is. However, you'll also notice if we press the back button, you can go to our previous plot, and as we can see, sadly, not all the rays are coming through. If we zoom into this section, you see that some of them are diffracting, are trying to diffract, are trying to come out, but they don't have any place to hit. And the reason for this is if ASAP doesn't see a ray as having an interaction, it will stop the source. So we have a quick way to fix that. Let's jump back to our source size, or rather our detector size. It's right now at 100. Let's jump it up to 300. Let's see how that does. So press apply, and we have a much bigger size now. Let's run again. And now all of them are hitting it. And you can actually see a much larger view of our system. And you'll see how they bend at different places. A source that comes, for example, here around the edge. This is our old system. Give me a sec. Also, this one is the one I believe we're looking for. Nope, this is the one. This is the wonderful thing about ASAP. You'll have to figure out which windows, you'll have to manage these windows, and remember, because the plots will continue to be on the same page, but some of these other generated models, they will take up their own windows. So you'll see this is our old one, and this is our new display. And you'll see that the ones that were closer to the edge here end up being reflected at a more dramatic angle. This is because the normal here is at a larger angle and the normal here is at a larger angle. So this is why you see some of the more outward ones deflecting outwards at the angles that they do. And with that, we have a very interesting source for you guys to look at and to study, and you can also use it for some of your lens designs, especially if you want to look at binoculars, cameras, for how you would deal with things like chromatic aberration, i.e. how lenses, because with real light, different, what's the word I'm looking for? Different frequencies have different indexes of refraction. So it's an important feature to keep in mind as you design future optical systems. Anyway, as always, we hope this was helpful. We hope that you will continue to use ASAP and consider us in the future. Thank you very much. Also, quick interlude. If you want to save your system in your workspace, be sure to press this icon here of the floppy disk from way back in the 90s. Not sure how many of you, some of you might remember that quite well. And let's call it Chromatic Cube. .sdx, press save. And thus we have our system saved here. And with that, be sure to always save your files. Always better to be safe than sorry.